Welcome all students to this course we call General Physics 1, 014 to 0111. So some of you may already attain this course, but some may not. So make sure if you have any inquiries, feel free to ask me via my email. I am Sorasak Phanphak. So I'm a lecturer from Physics Department, Faculty of Science, Kasetsart University. So what I recommend, I use these two references as the textbook for you. So one is the Sorasak and another one is Gerald Walker's. So it's fundamental physics. So you can use the older edition or you can use this up-to-date edition. This is our first chapter, Introduction to the Physics and Measurements. What is physics? So you may also already know about the physics already, but what I would like to emphasize, physics combined with the several things, but physics used for explain the natural phenomena. So there's difference between scale and speed, right? So if you think about the size of thing that you are observed, if it's quite like enormous, like the planet, right? With quite slow speed, you can apply the knowledge of the classical mechanics to investigate that phenomenon. But if the planet moving really quick, like in the satellite system, so you may use the relativistic mechanic to investigate the system, for example, in GPS. But if the particle or the system you would like to observe is quite small, so here this is the lovely size, and if it's quite small in like nanometer scale or lower than that, you no longer use the classical mechanic. You can use the quantum mechanic or quantum field theories to investigate the phenomena. So this is kind of like the overview of the field that you use the knowledge of physics to investigate. So there's a lot of things that physics can explain. But from this course, we will focus in our classical physics or classical mechanic. It's back from the Newtons to the thermodynamic and fluid theories. So this is what we're going to observe through this course. And what I would like to emphasize here is the limit of classical mechanics is depend on dimension and also the speed of what you observe. Supposed to be much slower compared to speed of light. So we will start with the physical quantities. So if you would like to measure the physical quantity, you should have unit or proper unit to each of the measurements. So we have three basic quantities. Here is the mass, length, and the times. Mass is what you quantify things. For example, like, okay, you have mass. When you weight up, you know the weight. We have M to represent the mass. We have L to represent the length. We have T to represent the time. So I will clearly have this as a, L here, right? With these three quantities, you can have unit out of it. But the way to derive unit, we use dimension to derive it. For example, if you have the mass and you would like to get the dimension of the mass, dimension is what you use for quantify the nature of that quantities. You check whether that are the same nature or not of the quantity you measure. For example, if you would like to check the dimension of the mass, the sign for dimension is this type of bracket. You have this bracket. square bracket. And the dimension of the mass ASM is represent mass in terms of dimension, right? For the length as well, if you would like to quantify the dimension of the length, the big L is the dimension of the length. For the time as well, if you would like to check the dimension of the time, the dimension is the big T. So this is how you call the dimension of each quantity. If the quantity have the property of mass, when you check the dimension, you're gonna get this M of it. If something have the length, have the width, you will have L out of the dimension. And also time, if you measure the times, you're gonna have the big T. So what dimension lead to? The dimension lead to unit of it. Unit. The unit of the mass in SI we call kilogram. So we rather use SI as the fundamental unit rather than other unit. So we can use, for example, like food for the length, but in SI we will use meter as a unit. And the time we will use second. These are unit in SI system, right? It is clear. So the way that you quantify the dimension and change to unit, you can cross-check whether the quantity that you measure have some relation about this dimension or this unit or not. The way to derive, you can use the algebraic method for checking it. You can plus minus with the same unit, with the same dimension, or you can multiply or divide in between dimensions. So you will see later in the derived quantities. This is another quantities we call the derived unit. So the derived unit is come from the basics unit that you have, and you can multiply or divide them to have some derived version of the quantity you're gonna measure. For example, the area is what you have width and length, right? Width multiplied by length, you have the area of it. If you would like to cross-check the dimension, so the way to check the dimension is using the blanket to cover it, right? The dimension of width is what you measure in length as well. So you have L out of width. And for the dimension of L is L. So finally you got L squared for this dimension of the area. But what else about unit? You know the unit of length is in meter. So the unit of area is meter square. This is how you treat two dimensions that multiply to each other algebraically. So for how about the volume? Volume you know as the area that multiply by height, right? So I put the blanket for the dimension already, right? Here, the dimension of the area is what you already got, L squared. But the dimension of the height also the part of the measuring length as well, right? So that L is the dimension of the height. Sorry. So you will get the unit out of the L. I will write this like this, L square L, so that you get L cubed, right? Power 3 is cubed that you got, so that you get meter cube for the volumes. This is quite look simple for you, right? But you can use this dimensional analysis for further complicate quantities and then you can define the proper unit for it. What else about speed? Speed is the change of the distance in time, right? The rate of the distance that you moving in the specific time. So is speed is s over t. So if you would like to find the dimension of the speed, that's the dimension of the distance, right? And time. So that you got L over T in this case. So the final unit you're gonna get from this is meter per sec, right? Unit we also think about other later, but mainly we focus only in SI unit here, right? How about the acceleration? Acceleration is the rate of change of the speed, right? Compared with the time. So the acceleration is the change of the speed compared to the time, right? So the dimension of the speed you already find out is L over T, right? And the time is 1 over T. So finally, you're gonna get the unit out of the acceleration from this dimension as meter per sec square. This is the example of derived unit. Most of quantity you measure is gonna come with the derived unit back from the basics unit or basics quantities. So make sure you can do multiply, you can do division of these quantity. This is the first example. Let's see whether we can check this equation, whether they are in the correct unit or not, right? They're supposed to be, if this equation can plus like do some addition or some subtraction to each other. If you would like to add or subtract, you should have the same dimension. It should have the same dimension. I will do like this. Same dimension. This is the key that we have learned from the past example. So you can check this dimension. This is the equation of motion, but we not learn about this yet. We will learn more about this equation in linear motion in our chapter 3. So if you would like to check the dimension of this equation, you can write down like dimension of S equal to dimension of V0, dimension of T plus 1 over 2, and we would like to check dimension of this as well, and dimension of A and dimension of T square. S is displacement. Displacement is a kind of distance, but we will learn this more. And displacement is the vector. Next chapter we will talk about vector more. So to find S here, the dimension of S is length, right? This is what we would like to derive the dimension. And the dimension can convert to unit finally. So this dimension of S. For how about V? We did find the dimension of V already, right? Because V is S over T. So the dimension is L over T. And multiply with the dimension of T is the big T. And you add up with another constant. 1 over 2 is constant. So if this constant, the dimension of constant is equal to 1. So there's no dimension. So you can write it as a 1 or just don't care about it. It depends on your choice. How about the dimension of acceleration? A is acceleration, right? We did file on it. Oh, sorry. There's some problem about my pen, so I will fix this later. Uh, the dimension of acceleration is L over 2 square, right? And T square is the big T square here. So what you gonna see here, now you can do some division. Oh, I don't know whether anyone have comment on it or not. This is the problem of the online session mostly. But okay, nothing happened. I got some like chat in our group notice, but nothing happened. But don't worry about it. But so back to this part. So now we got L equal to L O T multiplied by T. So you can operate algebraically here. You can use algebra that you learn, right? You can plus or subtract them. You can multiply or divide them. So, but mostly of operation, you don't need to plus or minus. The way to plus or minus, you will use the definition that we already have. If they have the same dimension, it can add or subtract. So with this case, you can like cancel each other because it's t square divided by t square. What you get finally, you get L equal to L plus L. So this is the dimension of the length on this left hand in this equation, and the right hand also the same dimension. So all these measuring things is in meter. Oh, sorry, meter, meter, and meter. So they are all in the same unit. So whether this equation is correct or not, the answer is correct due to the correct dimension. This is what we did investigate. So there are some lag between my writings because some internet signal. For the next uh, subject or next topics, I will do some record and then you can watch the video smoothly. Sorry for inconvenience. So for the next example, so what else about the below quantities? So can you use the dimensional analysis for this quantity? So this is like derived quantities, right? Okay. The way to use the dimension analysis, you have to know the relation of this back to the basic quantities that you have. For the density, you know, is low and mass over the volume, right? Density is equal to mass over the volume. If you would like to find the dimension, you just use the square bracket. The bracket, not blanket, sorry. Square bracket. And after that, for the mass, you know, the dimension is the big M, right? And for V, the dimension is L square because volume, not L square, sorry, L cube, right? Because the volume is from width, like multiply by length and multiply by height, right? So you got L of this, L of this, and L of this, so that you got L cube. It's also always happen like this. Sorry for. I'll write again. So this is the m over l cube, right? This is the dimension. So what unit you're gonna get? You're gonna get unit of mass is kilogram, right, per meter cube. So make sure you don't mix up between mass and meter, right? The meter is unit of the length dimension here, but the kilogram is a unit of the mass m, right? So you write this as dimension and this is your unit. Okay, next for the pressure, I'll remove this out. What is the pressure? The pressure is P, right? P is force over area. But force you will learn later. Force is the mass with acceleration and divided by area. So if you would like to check the dimension out of these quantities, I would like this. So you can have the dimension of mass and the dimension of acceleration and divide by the dimension of the area, which is mass that you have. Dimension is big M, right? For the A is L over 2 square, right? And for A is L square. So by this you can get rid of it because you can operate algebraically. So for the pressure, the dimension of the pressure, you can get M over L T square. And what the unit of these quantities of this dimension? So the way to write unit here, M is mass, right? So unit is kilogram per L is meter, T is sec square. So this is unit from the pressure. So you will learn later, like, because F can be newtons, but Newton is not in the SI unit. Newton is kilogram meter per sec square. So you can do that and convert to this. But later, we only focus on the SI unit for this dimensional analysis. How about the work? Work is force that make with some distance, right? Force with something made to the system at some distance. If you would like to find the dimension of the work, so you get the dimension out of it. And the force is MA, right? MA. Find the dimension of it. And S is here. So this is how you're gonna get the dimension of the work. M is big M, right? A is, you already seen it several times. L over 2 over T square. And S is also L. So you're gonna get the final dimension as M L square over T square. As a unit, you're gonna have this unit in kilogram meter square per sec square for the work. How about the power? Power is what you get work with the specific times. P here is pressure, P here is power. It's different things, right? You will learn more through this course. So if you would like to find the dimension of the power here, you already know the dimension of the work. So it's ml square over t square. And the dimension of time is big T. So finally, you're going to get ml square over t cube. This is the dimension of the power. So finally, you're going to get unit of this as kilogram as a unit of mass. L square is meter square divided by second cube. Right. These are all unit and dimension of the state derived quantities. Make sure you can do this dimensional analysis and find a proper unit in SI in the system.